Good morning, good afternoon, and good evening, wherever you are. Welcome back to another CIQ webinar. My name is Zane Hamilton, and I'm the Vice President of Sales Engineering at CIQ. We at CIQ are focused on powering the next generation of software infrastructure, leveraging the capabilities of cloud, hyperscale, and HPC. From research to the enterprise, our customers rely on us for the ultimate Rocky Linux, Werewolf, and Apptainer support escalation. We provide deep development capabilities and solutions, all delivered in the collaborative spirit of open source. Today, we've got a really exciting webinar for you, a learning series around containerization, and we're going to present a case study running on a new application. If we could bring everybody in, that would be great. Welcome in, everyone. So most of these faces should be familiar, but we have one that's not. So Eric, would you introduce yourself and tell everybody who you are?
Hey, hello, thanks, Zane. So yes, I am Eric Loquignou. I am responsible of Radioss development. In fact, I started in Radioss 28 years ago, so a long time. And yes, and started with developing the parallel version of the code. This is my specialty. So high performance computing applied to a mechanical engineering solver. And I am really pleased to be here and to talk about a new project that we started 1 month ago, which is OpenRadios.
Fantastic. Thank you, Eric. I'll let everybody else introduce themselves and we'll dive right into it. Dave, you're next to me, so I'm going to let you go next real quick.
Hey, everybody. I'm Dave Godlove. I used to be a neuroscientist, primary researcher working at the National Institutes of Health. Since then, I became interested in high performance computing, and through that conduit became interested and started working in containers, the Singularity project, which ultimately became Apptainer. And so I'm glad to be talking about this newly containerized application today. This is really cool.
Thank you. Welcome back, Dave. Brock.
Hi, I'm Brock, HPC here at CIQ, but longtime colleague of Eric. Thrilled to have him on today. He is a bona fide rock star in the simulation world and has been driving a lot of different things through the years. So, just a little more context. We got kind of involved in a project really quickly with them in this latest adventure. So I don't want to say too much and steal too much thunder, but pleasure to be here. And again, Eric, thank you for joining us.
My pleasure.
Thanks, Brock. Jonathan, I feel like it's been a while.
Maybe. But yeah, happy to be here. My background's in HPC systems administration, and with CIQ, I'm on the solutions architect team. We do our best to put together cool solutions like this for customers and demo purposes.
Thank you. Forrest.
Good morning, everyone. My name is Forrest Burt. I'm an HPC systems engineer here at CIQ. My background is in the academic HPC space. I was a system administrator on some high-performance computing architecture and a member of the research computing team at a major American university for a while. And now I'm at CIQ, where alongside Jonathan, Dave, and our solutions architect team, work on building out cool stuff with open source and HPC. So very happy to be on. Thanks for having me.
Great. Thanks, Forrest. All right, Eric, let's dive right into it. Tell us, what is OpenRadios?
Yeah, that's a good question. And in fact, just before, I just want to explain what is Radioss. So Radioss is a standard for crash and safety since more than 35 years. So it is used by car OEMs to build 5-star safe cars. It is used also in aerospace, in consumer goods, electronics, defense. In many applications, every time there is very highly nonlinear dynamic events when only explicit solution can converge. Okay, so that's really the aim of a code like Radioss. And in fact, beside all the capabilities developed during 35 years, we have seen that more and more the new innovation in the code are coming from a partnership between academic researchers and industrial partners. And this is why we think that with the rapid transformation in the transportation industries, thinking about more sustainable energy, thinking about autonomous vehicles, we really need to innovate faster, to increase the space of innovation based on collaboration with best scientists around the world, best specialists, to address the challenge that the industry customers encounter in their daily project. So, and we think that having an open source version of Radioss is a fantastic enabler to do that. So, you know, with OpenRadios, we offer to the community the access to 35 years of great libraries of element of interface in many, let's say, libraries that you can use, and then you can really focus on your research. This is the aim of OpenRadios, to provide this fantastic platform to the community, and then to let researchers doing their research. And in fact, the important thing is that then, if we have those research in OpenRadios, the knowledge of the team, of the development team, is how to bring those research, those proof of concept, to industrial feature. And this is really the plus of the team, is to provide this platform for the research, but at the same time to maintain a high level of industrial software like we did in the past, but now we can do it faster with all the community with us to innovate faster. So this is really the aim, and I think this is why we want to maintain two versions. So OpenRadios, which is now available to the world, the open source version of Radioss, and Altair Radios, the commercial version that is here with, let's say, additional maintenance, additional robustness, with versioning, with things that we don't want to compromise. That is, at the same time, to have the best of state-of-the-art research, and at the same time, industrial products that we will continue. So in few words, this is OpenRadios.
It's fantastic. Thank you. One of the questions I have, I know we've talked a little bit about simulating automotive crashes. What else are people doing with this? I'll open that up to anybody.
Well, I can jump in. So the OpenRadios.org site actually has a lot of models on it, and there's one I keep advocating we go do, and that's the model of the soccer ball hitting the goal post or hitting the crossbar, and then modeling whether the deflection bounces into the goal or out of the goal. And I forget which match this model was particularly talking about, but I also remember, I think England winning the World Cup maybe have been a similar situation. And I think they even saved the patch of grass that the ball landed inside the goal. But there's that, there's a cell phone drop model. So again, you know, what I love about the selection of models, Eric, that you picked, or Altair picked when you stood it up, is it's not just those car crash models that in the HPC space are really well known, but it's the element of product in almost any space can benefit from simulation. And again, cell phone, if anybody on the call has not dropped their cell phone once, I challenge you to raise your hand because I know I've dropped mine multiple times.
I run that simulation frequently in real life.
Yeah. You know, and think anything that actually ships in a box, you know, a box drop, what's the packaging inside, the box design itself. You're talking about the cases of simulation that are quickly spreading to everyday life, not just the, you know, design an airplane wing or something of that nature, high-end HPC that we've talked about, but
so just to complement, that is, of course, at the beginning it was in the defense that code like that were emerging. Then the automotive industry adopted such technology, and then with the progress in terms of hardware, what necessite in the past a big computer, you know, Cray, vector machine. Now you can do simulation, I would say, with your cell phone. I mean, maybe not today because we didn't port it on such a OS, but I mean, this would be as powerful as the old Cray, you know. So now a wide, let's say, domains can use Radioss. As I said, every time you have some, let's say, highly dynamic event, highly nonlinear event, and believe me, a cell phone drop test is something very difficult to simulate because you have so many small pieces with some intersections, not always a very clean mesh, because those guys, they need to advance very fast their research and to do crash very, very fast. So the code has also improved from years to years to be able to handle such cases, which are also very complex, even if they are, let's say, maybe less impressive than a car crash. And for the match, it was Saint-Etienne against Bayern, a very bad souvenir for French guy.
That's great. Thank you. All right, Dave, since you're the container guy around here, I'm going to ask you, why is it important to containerize this?
Well, I think Eric just provided a really great reason. It's really great that we have this opportunity to take, the software now that it's been open source and to be able to leverage all the benefits of containerization that, have been applied in a lot of other domains now, but, not only like helping out, people who are using this software, but introducing this whole new community now to the benefits of containerization and the benefits of using this. So Eric was just talking about how, this code, it used to be that you would just run it on some huge dedicated Cray system long ago. But now, I mean, you might run it on your laptop, you might run it on a desktop system, you might run it on the cloud. In the future, maybe you might run it on a cell phone or who knows what. And so if you've got this thing containerized and you can, easily port it from one place to another, that's one of the great benefits that you get from containerization, is just being able to, duplicate and run the same code in multiple places. The demo that I'm going to be running through today, that Yoshiaki Senda had put together, that demo I actually ran on my own laptop. So, but since it's containerized, I could take that same demo and, put it up on the cloud or run it on an HPC system or whatever, and, instantly get the benefits of more computational horsepower. It's also great too, because, so OpenRadios is not, it's not terribly complicated as far as dependencies, but it's not, it's not released as a precompiled binary or anything either. So you do have to do a little work to build it and to put it together. And, down the road, this might be something that, can be put up on a registry that somebody, instead of like installing it on their computer and doing all that, or even building a container, can just grab the pre-built container and run it as is. And that's another great benefit that is used, quite a bit. And then when we talk about like the choice of Apptainer in particular, I mean, I don't know if you wanted me to.
No, that was my next question is what is the right container platform to do this in? Because we've talked about Apptainer a lot and how easy it is to make it portable. Kind of to your point, well, why is Apptainer the right choice for this?
Well, does anybody else want to jump in and riff a little bit more on containerization in general, and why it's the right thing to do here? Is there anything I missed, maybe?
Well, I'll tack on it. I think you said it, but especially in a manufacturing world, in a commercial world, what the container helps do is maintain those versions that you're using. So if you need to go back and repeat results, you've got a container that's built on a specific tag of the source tree. You're going to update over time, presumably, but you can retain those containers. So you can always go back and use older containers to verify previous results. And depending on the case, that could be very, very valuable in a design process. If you're a researcher, obviously being able to distribute the container that you're using so other people can verify your results is also highly beneficial. And again, you need that reproducibility, and Apptainer helps satisfy some of those needs, right? And as well, I'm half side tangent, but it's back to something Eric was hinting on as well, or hitting on as well. the environment we're in is the pace of new silicon and technology is coming fast and furious. And when I first heard that OpenRadios was going open source, I thought, well, this is a really gutsy move. But it quickly went from, this is not gutsy, this is brilliant, right? Because you're talking about multiple CPUs now, multiple CPU architectures. Each vendor has special things that they're introducing inside of CPUs. You've got stacked cache, you've got high bandwidth memory, you've got all these different aspects that developers are having to think about. Then you've got accelerators, and all three of the major silicon providers have their own accelerators with their own special software stacks that you can go through. So again, it's just permutations of all these things that developers have to face. And Eric probably keeps you up at night sometimes, right? So pushing this out into the world like this, putting it out there for people to contribute, gives a way to come in and actually increase the speed that you can respond to the advancements that are coming fast and furious in silicon. And who knows what custom accelerators are around the corner. We talked last week, I think it was, EDA is a booming industry. So as a developer, you've got to handle all these different things that are coming and pick and choose where you go. By having a community, the professional Radioss clientele or that community is going to benefit greatly from the rapid advancements that can come through the open source community, but still have that professional service around it. So I think containers, to wrap it back, really help distribute those different versions. And it's just going to help increase the reach of people being able to get into simulation with Radioss and actually move to varying levels of how they can use it. And again, it's highly complex to do this kind of work, but it just, the future is as much as you can put into it. And we're helping ease the technology integration for those users.
Yeah, and if I can add 2 words, I think it's a fantastic example, this contribution, for 2 aspects. First, because it illustrates perfectly one thing that we want to do with OpenRadios is that to facilitate and to make an accessible software. And I think containerization is a great example of making the software more accessible to a wider numerous community of people. We are still a little bit old school. We develop with script, with things like that, and we think that everyone can do that very fast and very easily. But I mean, it's not so easy. It's old school. With container, you just launch your container and you have everything that has been already set, and you can redo it, let's say, instantaneously. So it's really nice. And the second thing is also how quick you did it. Because I think that this is also the power of this community, that we have everyone that jump on it and put innovation like that in many different domains. And for me, it was, wow, they did it in over 1 weekend. And yes, I really want to say big thanks to Yoshi-san. But I mean, it's incredible to see that after the first weekend, after the launch, I think I saw that. So it's wonderful example.
Yeah, I'm going to echo that. Yoshi-san, I mean, he did it faster. It took us longer to do the write-up of what he did than it took him to actually get the container up and running and show it running. And of course, we did it on Rocky Linux as well. But it was really fast, right? And that, again, it just speaks to the brilliance of making this move. I think it's going to pay huge dividends for everybody because it's going to bring a lot of people in.
It's fantastic. Thank you guys for that. So I'm going to go back to my other question of why Apptainer. I think this is the interesting part. I'm going to pick on Jonathan because he's staring at me.
I mean, Apptainer makes a lot of sense for this kind of application because of the kind of, first of all, it's a batch processing application, at least as far as I've seen it. Makes sense with Apptainer's execution model versus other container. There are other batch processing container execution systems, but Apptainer is kind of the most well publicized, well distributed, as far as I'm aware. And then there's also just performance benefits from SIF as well, especially on shared file system environments. These are things we've gone over before. But it also just makes it really easy. And that's, most container systems are pretty easy, but especially with recent developments in Apptainer, doing unprivileged builds, being able to turn those over just as a regular user. Anyone on most modern HPC environments could do the same work with the same full stack customizability of your deployment environment, the OS and libraries that you need to bring in for an application like this. It just makes it really easy to get up and running in any environment.
That's great. Thank you.
Yeah, and
Dave,
if I want to
no,
just to have one comment, if I remember that I saw Singularity, and I think Singularity is, it says, the father of Apptainer, and I remember my having seen that at SC something, and yes, and see how the benefit for a large MPI application to run on Apptainer. On I mean, Radioss is compute intensive and aim to run on large clusters of MPI, so I think that's a great choice to start with containerization.
Thank you, Eric.
I just want to ping on that just a little bit. There's a couple more things too. So, I mean, one thing, yeah, so Apptainer is just the perfect fit for this, right? I mean, it's an HPC, it's a process. It's not like a service that's supposed to run. It's an HPC computational process. It's you get benefit from running it as an executable, which I'll show a little bit in the demo. So you get benefit from running the container itself as an executable file, because the way that it integrates with the container run system. It, and it also interfaces, as Jonathan kind of mentioned, and Eric kind of mentioned too, with MPI. And Apptainer kind of famously was pretty much through Singularity, its predecessor was, famously like the first container solution that was MPI aware and that integrated seamlessly with MPI. Some of the great work that Jonathan's done recently has allowed you to run containers with MPI completely containerized now through Apptainer. And I mean, there's a visualization component in which GPUs might become important if you're using like ParaView to visualize these simulations. And so now you've got the seamless integration that Apptainer has with GPUs. So it's just like, it's bread and butter, exactly what Apptainer was made for, pretty much. It's the perfect solution for it.
I'm curious, Dave, real quick, the visualization part of it, is that something that you can ever visualize in real time, or do you run your simulation and then do the visualization after the fact in all cases? Or maybe Eric can speak to that too.
Yeah, maybe I can speak about that. In fact, when we run Radioss, in parallel, Radioss is generating animation file. So it's possible to load your animation file at the same time that you run the simulation. So you do not need to have the simulation finished. You can load the animation, but it's not real time, but you can, let's say, process the animation on sometimes people do that because if you see that, for example, your simulation is not going in the way you want, you can stop it, change things, parameters, and rerun it. So having, let's say, some interaction between the simulation and the animation is good. Yes, this is nice to mention ParaView because, I mean, this is also one aspect which is important with OpenRadios, to be open toward many applications. So while HyperWorks is the best pre and post processing tool to run Radioss, which is an Altair product, commercial product, we now also offer interface to ParaView on VTK. So we have a converter, so you can convert your animation at the same time they are run by the produced by the solver, and to visualize them with ParaView with let's say a complete open source workflow.
Yeah, that's really cool.
One more like really quick thing too, just like from a cultural standpoint. I mean, like, so the Singularity community, the Apptainer community, CIQ, all these organizations exist really to support like people first, right? And are very like people oriented and people centric. And, we develop software, but we develop it with people in mind. And so because of that, I'm super excited about this, type of software being something that we can really support and jump in and partner with Altair on. And because we're realizing that goal of really, I mean, in a very concrete way, we're helping to make the world a safer place. I mean, it's great, right? That's exactly what we're trying to do with this software.
And speaking directly to the value of OpenRadios as an open project, like, Brock put a thing in our internal chat on, hey, it would be cool if we could containerize this. Immediately, everyone agreed, and there were multiple people working on it at the same time. Yoshi came out with a successful deployment just really quick off of that. But immediately, that was turning back around to trying to contribute to the project. And hey, these are things that we've learned. These are things that we think would improve the build system or the build instructions, things like that. And it's really great to be able to collaborate so immediately and so quickly, right after, just days after the project was started. It's been cool.
Fantastic.
So
I think it's easy to see, that what we did first was just, I'll say the basic options, but GNU compilers and things of that nature. But if you want to build optimized versions for whatever platform you're running on, again, that takes a lot of different elements of using the right compilers, the right options, and lots of effort. And a community is able to get the different people involved to put those branches in place. And again, something like Apptainer makes it easy to capture exactly that one thing for what you need, and distribute it and use it and curate it, if you will. Again, the real value here is, again, I think that what you're going to see is more professional Radioss users moving that direction, because they can get in and use OpenRadios to figure out how to fine tune how they use it. But everybody at the end of the day is focused on designing and using the software as a tool. And I think you're going to see the revenue base for Radioss increase. That's why I've gone from thinking this is a gutsy move to this is a brilliant move, right? And again, I think Dave, you said it. Or one of Jonathan, Forrest, we've all said it at some point. Simulation, the more it's used, the better and the more innovative things are going to come out, right? And it's we can't think of what's going to come out if we get this in the hands of more creative type people who have this type of access to this type of tool.
And we really want to democratize Radioss and the usage of such software for a wider community. And this is what we see with the open source, with your initiative, with other initiatives. We have seen crazy things done with Radioss that are really wonderful to see in so quick time. Yeah.
Thank you, Eric. I guess now I'm going to ask Dave. As Brock posted this as a question, wouldn't it be cool if, how did this actually get done? How did Yoshi go about doing this and containerizing OpenRadios?
Okay, yeah. So it's great you've asked. So I've just tried to share my screen here. There we go. Great.
There it is.
So yeah. So let's dive into this a little bit. So this is a blog post that was written by Yoshiaki Senda and a few other people, but he did the technical work on it. Yoshi's name has come up a few times now. I just want to make sure that we give him a shout out and say that this is really his work that I've got the pleasure of going over and talking about today. He is in Japan, so it's really, really late for him. So that's why I'm going to be presenting this instead of him. But yeah, he deserves all the credit for this. This is really great work that he did really quickly. So we'll post, I'm sure, a link to this blog post. I kind of picked this up a couple of days ago and went through it in detail, and I was able to run this with very little effort on my laptop and get the simulation running overnight. So I'll kind of show you how I did that, just sort of following along with this post here. So of course you've got to install Apptainer if you want to run this container. If you want to build and run this container, that should be pretty straightforward. That you have to do that, and there's some information there for how to do it if you are unsure. And then Yoshi has posted this definition file, but there's going to be some departures also in this demo from what's actually put here. And we're going to, I think, update some of the things in this blog post. So since this blog post was created, Yoshi actually created a pull request upstream to the OpenRadios GitHub repo, which has been accepted. And so you can get the definition file straight from the GitHub repo now. You don't have to like copy and paste it here. And it's got it's a little bit better, or a little bit improved over what's been posted here. So let me just go ahead and jump over to my terminal where I'm most comfortable. I am in a directory called Data Containers OpenRadios. I have some data here, which I will look at later, but for right now, we don't have to worry about it. So following along with that blog post, the first thing that you have to do is just go ahead and grab, the upstream repo like so. And once you do that, you can CD into the Apptainer subdirectory, and you will see the definition file right there. And so you can just go ahead and use this to build your container, using Apptainer right from the get-go. I'm going to show you a few little things, a few little tweaks that I would make in the definition file, but you can build this just the way it is as well. Either way works. The definition file is great as is. There's a make here, which has this -j option, and it's empty right now. So I think that the intention is you would go ahead and put the appropriate number here, depending on how many cores you actually want this to compile on. Maybe I should go through the definition file a little bit. So we're starting here. We're going to pull a container from Docker Hub as a base. And the container that we're going to pull is Rocky version 8. So this is going to run on a Rocky 8 base. If you're new to Apptainer, the definition file consists of a header and some little scriptlets, which all begin with this %sign, and then have a keyword. This scriptlet post happens after you have the base container set up from the header. So post, setting up the base container. And here what we're doing is we're using DNF to install development tools, and then to install basically a bunch of compilers and a bunch of dependencies, just standard things like wget and git and patch and stuff that you need in order to make these things work. We're going to CD into the temp directory. It's notable that it's something that you should note when you're building containers with Apptainer, that the temp directory is shared between the container during build time and your host system. So if you CD here, you're CDing into a shared directory. We're going to download some MPI. We're going to untar the MPI, CD into it, and then we're going to compile it, configure it and compile it and install it. And then we're going to CD into opt. We're going to go ahead and enable some large file system goodness from GitHub so that we can, download some big stuff from GitHub. We're going to clone so it's kind of funny because I've already cloned the repo, and I'm actually inside the directory which was created when I cloned the repo, and now we're going to clone it again, but this is actually going to be inside the container, and this is going to facilitate us being able to build this package. Now here's one of the places where I would do just a few little tweaks, and I'm going to tell you why. You don't have to. So what we're doing here is we're building from the main branch, and so in development, main, well, it depends on your development model. Some people use like a different branch, like a development branch or something. But a lot of times main is the development branch. And so what you're going to get here is the latest, greatest, bleeding edge, version of OpenRadios, which might be what you want. But for reproducibility purposes, or, just because it makes it easier to kind of go back and see what you've done and, maybe alter it, I would suggest, here's what I'm going to do. I'm going to go ahead and copy that line, comment this one out, and I'm going to remove the depth equals 1. And what that's going to do is it's going to allow us to get multiple commits when we download it, not just the last commit, but multiple commits. And then what I'm going to do, oops, yes, let me save that. Let me get back out top, and I'm going to use git log to see what the most recent commits are in this GitHub repo. All right. And so I see that this is the commit that I'm actually on right now. I'm going to go ahead and copy some, the beginning of that hash. And then I'm going to go back into that definition file. And I'm going to, after I cd into the Git directory, I'm going to do a git checkout and then that hash. And what that's going to do is it's going to pin this definition file at the current version of OpenRadios. So if I have some kind of a bug or something like that, or if I want to reproduce this build later on, if I run it the second time, it's not going to be a different build. It's going to be exactly the same build. But that's just a suggestion. You can also build from master if you want latest greatest, or if you want to just like update your build every time. Okay, and so now we're cloning the repo. We're going to cd into it and pin it at a particular place, and then we're going to use the scripts which come with OpenRadios to go ahead and build it inside the container. We're going to cd into several different places and do that, and then there's several environment variables which need to be set up. This section %sign environment is going to set those up for us and make sure they're always there every time, and that's pretty much it. So this is it's less than 50 lines long. It's not an overly complicated definition file. I will say there's a lot packed into that little definition file. There's a lot of compiling. There's a lot of computational work that has to be done based on that little definition file. Oh yeah, and there's one more little kind of gotcha little thing that I wanted to cover here as well. And that little tiny gotcha is that so you notice that we cd'd into temp, and then we started to compile things. On many systems, temp is mounted to the system in such a way that you're not allowed to run executables from temp. It's just a safety consideration. Temp also, depending on what your environment is, might not be that big. And when you're creating containers, you need several times the size of the ultimate container to be able to create it, because you create copies of it, you move it from one permutation to another. So because of that, you might run into trouble if you just run it as is. I would suggest you set this environment variable, Apptainer temp dir, and you set it somewhere else. var temp would be a good solution to this, or a good place to put that. And after you do that, what that's going to allow you to do is run a build with the fake root option. So you don't have to be real root, because you don't need to be able to compile or to run executables or do whatever in temp anymore. And I would just go ahead and do that. And that way you're not also going to overflow temp. You're not going to fill it up or whatever. Okay, so we're going to go ahead and do this. I'm not going to go through all this build. I'm going to, I'm sorry. Also, this is kind of an unsafe thing that you need to remember to do. Make sure your bind path is not set, because in recent versions of Apptainer, you can actually bind directories from the host system into the container at build time, which can be pretty dangerous, actually. So let me try that again. This is going to take a while because my system is not, is not very powerful, and there's a lot of computational work to do here. So I'm just going to Control-C out of it, and I'm not going to go to completion. But I made these changes earlier today, and then I double checked that I could actually build the entire container from start to finish, just to make sure that I didn't introduce any bugs, and it seemed like everything was okay. So that's a quick and easy way to get the definition file instead of copying and pasting it from here. You still can copy and paste it from here. This one works as well. And then you can, just build your container and get moving. Do we have any questions or comments on that? I've just been like blabbing.
Not yet, Dave.
Well, we can comment, as Eric said earlier, this code is something that actually used to be targeting Cray supercomputers and things of the like. So the fact that it's actually running on a laptop is quite remarkable through the years. But again, it's the number crunching part that can take a while. We have to do that time elapsed thing, or we'll just be sitting staring at the screen.
Staring at a lot of Fortran building. Yeah.
Yes.
Which is cool. It's cool to see my laptop building Fortran. So one of the cool things that Yoshi suggests that we do here is copying the resulting CIF file to a place on your path, so you can run it as a binary. So I'm just going to clear all this off the screen. So I've already done that. So if I say like which, I just called it OpenRadios, and I copied that into my home bin directory, which happens to be on my path too. And so now I can just call it, which is, pretty helpful. You can just, run it as an executable, which is pretty helpful. Okay. And so then let's see. You don't have to be, actually, I guess you could run this without MPI, but if you want to run it with any kind of speed at all, it's important to have MPI installed on your system. So I went ahead and did that as well. There's a bunch of data to download. So maybe I should back up. I didn't actually talk about, the introduction, what this is and what we're doing. I just dove right in. So this blog post is really cool because it's taking a real car, which has really been modeled in what looks like a lot of detail, and it's going through a car crash simulation. This is I think it's a 2012 Toyota Camry. Yeah, it says right there, 2012 Toyota Camry, that it's crashing. And then afterwards, you have like a ton of data about, what parts of the car were stressed during the impact, and, what forces like the front bumper experienced versus the cabin and stuff like this. And so it's really, really cool to be able to run this simulation just like overnight on my local machine. So here are all the data that you have to download, which include like the model of the car and, include all the bits and pieces that OpenRadios needs in order to do this simulation. That was that little directory, by the way, that I told you I'd talk about later. I've already kind of cheated and downloaded that ahead of time. There's this module load command that kind of assumes that you've got some stuff installed on your system. You can do the same thing, actually. Let's see. Jump back over here. So I just added this directory to my path, and that seems to be sufficient, at least for what we're doing here today. So that kind of takes the place of that module load command, because I don't have modules installed on my laptop. And then now we're to the actual show, the actual cool stuff to do. So there's a couple of commands here. The first one sort of sets up the problem. And Eric, jump in anytime, because I'm not going to be probably explaining this properly, but I believe that the first one sets up the problem according to the number of processes that you want. And
yes, exactly. I can explain if you want. Yes. So here, in fact, we specify the number of MPI process that we will run. So in fact, the starter is, let's say, a pre-processing tool that will read the data and then do some, let's say, initialization, checking, and prepare what we call the domain decomposition. So we run the domain decomposition, and we will build from the starter so-called restart file, and then the simulation, the engine, will start directly with its local memory on 8 MPI processors.
And I was going to start it while you were talking, because I thought that might kind of illustrate what you were talking about.
Yes, and maybe I can add one or two things, because I mean this tutorial from Yoshi is really wonderful, because it shows also that you can directly download this model. I think it is downloaded from the CCSA website, and it is downloaded, in fact, not a Radioss model, but LS-DYNA input deck. So another, let's say, software well known in the explicit code. And in fact, Radioss is able to read this popular format. So in fact, here we are able to directly read and process the model with Radioss from, let's say, this format and this model which is available on the net.
Cool. And you may have seen too that I experienced a little error when I first started this. And that is the reason, I don't know if I'm going to have the buffer. Yeah, okay, I do. Good. Okay. Ooh. So I experienced a little error here when I first tried to do this. It told me, you're in trouble. You can't run this. And the reason was that it said that it couldn't find this input key that I gave it that as instructions for setting this problem up. The reason it couldn't is because for whatever reason, my current working directory wasn't properly bind mounted into Apptainer. It just tried to drop me into home instead. And so you can solve that. If you do run into that issue, you can solve that just by exporting the Apptainer bind path. This is why I had it set previously and why I almost got into trouble when I was building the container. You can set the Apptainer bind path to be the place where you currently are, where you've got your data.
And I think that's typical of Apptainer runs, isn't it? That it only binds in your home directory. So if you've got something outside of it, you would have to do that explicitly, like you've done.
It unfortunately depends a little bit on the version of Apptainer.
Okay.
That's something which has kind of been a little bit buggy sometimes. It is supposed to bind also your current working directory, and under certain circumstances it does. But I think that it might kind of choke on that if you have if your current working directory is a long nested subdirectory. It might only get to a certain depth or something. Or yeah, I'm not actually totally sure.
Fair enough.
Cool. Okay, so we have 0 errors. We had some warnings, but we're okay with that. And so this, is basically, I guess, Eric, reading in the model and reading in the specifications of the problem, and then taking that problem with the model and splitting it up, actually, into these different files, which can be used by the different 8 processes that I specified in order to set up the MPI problem. Is that kind of an okay?
Yes, exactly. And in fact, just to add that the demand decomposition is fully automatic. So we have, let's say, heuristic to decompose and optimize the decomposition. And then the advantage is that you can run the engine directly with its own, let's say, data. The data are already split, and then the simulation can be processed with the 8 MPI.
Cool. And so that's exactly what I'll do next. So I've got this MPI run command that I've got saved in my history. When I actually did this with 16 cores instead of the 8. But then, my computer only has 20 cores in it. So I was being a little bit risky on whether or not it was going to be able to handle that okay. But it did with no trouble. And it ran overnight. I'm only doing it with 8 right now because I don't want to, I'm streaming video right now and I don't want to get all max headroom and whatever. But okay, so I'll go ahead and start this. And like I said, this would, when I ran this with 16 cores with this particular model, it ran overnight. So obviously I'm not, with 8 cores, I'm not going to be able to show you this entire demo from start to finish. But I have done it already, and I can kind of show you the end, by jumping ahead. But this is what it would look like. And it's kind of cool. Let me open up a new terminal window. Let me make that bigger so y'all can see it. If I run a PS right now, I can see that, I've got my MPI running. And this is, one of the benefits of using Apptainer is because I have this MPI running, and then underneath of it, you can tell this is an older version of Apptainer because it's just running this starter SUID script. But this is the script which spawns each one of my containers. So I actually have 8 containers set up by Apptainer, which is familiar with and understands the MPI command. And then it's orchestrated all the wire up and everything, within the containers by exposing them all and doing all the right things. I think Jonathan and Forrest can both talk a little bit more intelligently about what's happening under the hood here. And, this is where Jonathan has really done some great work as far as, not just doing this on a single node on multiple CPUs, but doing this across nodes and doing it fully containerized, right? So you don't even have to have MPI installed on your system. So I don't know if you guys wanted to comment a little bit on.
Yeah, sure. So ultimately, an MPI starts up multiple instances of your application and then assigns each of them an integer rank that your application can use to differentiate what part of the workload it's going to be responsible for, and then they can also communicate with each other by rank. And the struggle with MPI and containerized applications in the past has been that you need to start your application somehow, usually with a runner like MPI run, like what Dave is doing here. And that runner is usually bundled as part of your MPI implementation. So there's an MPI run or an MPI exec that comes with OpenMPI or with MPitch or Intel MPI or any of these. They all have their own starter. And historically, that starter has been kind of proprietary and bundled with it, and it knows how to start up its own MPI, and that's it. More recently, and I think more recently means in the last decade or so, but more recently, there have been efforts to standardize that process management interface, starting out with PMI1 and PMI2. These are well supported in queuing systems today. And the most recent effort for the Exascale project is PMIX to try and establish new ways not only to start up hundreds of thousands of processes simultaneously and performantly, but to monitor them when things go wrong with them, because it becomes a real problem. And so we're trying to rebase some of our containerized MPI work on these standardized interfaces, so that instead of needing an MPI runner outside your container that is conceptually coupled to the MPI implementation that your application is built against inside, the only interface is that PMI standard. And using a queuing system like Fuzzball or any other would know how to speak that protocol and would not necessitate bridging that gap with a specific MPI implementation, which solves a lot of the problems that people have been having trying to do this. It doesn't quite apply here because without a queuing system, you don't have a PMI client to run it with. But so, you're just using the MPI run that comes with OpenMPI because it
right, but it does kind of apply, because at the end of the day, from a user's perspective, what this is going to mean is that you can take this container and just port it from one place to another.
Yeah.
And then just run it with your MPI commands pretty much transparently, and it's going to be able to spin up either on your laptop or either on an HPC system on multiple nodes or whatever you need it to do. So a lot of times what people do is they sort of they develop their containers and they run them locally like I'm doing here. This would be like the first step. And then you say, okay, now I got something really big I want to run. And you scale that up and you bring that out to an HPC system or up to the cloud or whatever. And then, run it in a bigger way. I need to point out here that I pressed Control-C. This was not like a bug in the program. It's just, I heard my fan spinning up. Yeah, I saw you looking, Eric. And I was like, no, it's okay. Yeah, I hit Control-C because I heard my fan spinning up, and it was doing its good work, and but it said it was going to take like 36 hours. Yeah, all those Control-Cs. It said it was going to take 36 hours to complete, and so I said, well, that's a really long demo. So instead, let me just jump over here. Now I'm on a different machine, one with a GPU in it. And I've also got ParaView installed, the ParaView viewer installed, and I just want to show you some of the actual fruits of this labor. So you could go ahead and do something like this. So I've got, these are all the different, these are like different time steps within the simulation that were saved in as like 3D models, which can be rendered using something like ParaView, which you can then step into and look around and try to figure out what was happening at a particular point in time. Okay, so I'm gonna go ahead and jump into this. It's always a surprise as to where the screen actually pops up at. Okay. And it's going to go ahead and load that, and then we're going to be able to actually see this car crash model and what it was doing. Okay. And so there we go. Oops. So we can zoom in on it. And I haven't played actually extensively with this yet, so I don't really know all the stuff you can do, but it looks like this model is really, if you like, you can take the opacity on this thing, for instance, and you can move it down, and you can see, like, I mean, this is a very, very detailed model, I assume, with lots and lots of different materials in it. So as you're running this is my first time, so bear with me a little bit, but this is my first time, running these types of simulations. And one of the cool things about them is, so as you're running them, you start getting these messages that says like this shell ruptured and this thing, and basically what it's telling you is, I am modeling a crack in this particular material. I'm modeling, I don't know, maybe your oil pan just cracked, or maybe your radiator just split open, or maybe this is a new crack in your windshield that I have to model and then update the material, update the positions of the material. I guess it's like tensile strength and all this kind of stuff, as I'm going through. And so it's a really complex and detailed problem, which is solved here. So yeah, I'm just going to geek out a little bit.
I did look at this model, Dave, and it's got 1,086 parts in it. So yeah, incredibly detailed.
And that's probably not detailed enough, right?
Probably not.
So in car design, especially in crash design, big improvements here. The engines are designed to absorb and push down in a frontal crash like this. There's other views that get rendered as well that shows where the stresses and the strains occur. And you can actually see the colors and how the forces are mostly being directed around the cabin, not into or through the cabin. And it's the same way with the back. So I've had the pleasure of actually being in a crash where I was the middle car that got hit from behind and shoved into the car in front of me. And both the front and the rear of the car did an accordion, but the cabin was mostly untouched. So yes. Yeah, it's amazing what you can see. And of course, we put a lot of crash test dummies out of work. Their digital twins are now doing all the work, but it reduces the need. You have to physically crash this car. You're really just validating that the simulation is correct.
Yes, exactly. And what is important is that you can, at the early design of the car, you can, let's say, look at the simulation of the future behavior of the car. So if you want that you have some risk somewhere, you can change things at the early stage. Because if you wait to have a prototype to crash a car and you realize that you have an issue, then it's millions of dollars that you need to change the things at the last minute. So if you can do it at the early stage of the design, it's very nice. And also you want a greener car and safe car. So safe car means you need to be sure that you have no intrusion into the cabin and the occupant. But a green car means you need also to optimize the mass. So you need to reduce the weight of the car, where you keep a car which is very safe. So this is the objective of what you can do at the early stage, and you can iterate, running different samples with different change in the modeling across your cluster, and running many examples of the radios to do that. So this is the idea behind the virtual simulation, to optimize your model at the early stage.
These are the things that Brock was talking about, as far as like, so I'm not familiar enough with ParaView yet to be able to put on the right colors and be able to view this, but this is a model, one of the some of the data that are saved there in the simulation, which gives you where the stress is at. And it's very nice here to see that the stress is actually mostly in the front and then kind of carried through the frame, and is not in the part of the vehicle where the occupants are.
So just a picture of Brock's car.
Oh.
Yeah.
Once again, I walked away from it. I was in shock and did not have. I had my camera. I could have taken a picture, and I didn't. But other than the shock of being in that kind of an accident, I was very thankful for designers who use simulation.
And once again, thank you so much to Yoshi for putting that together and making it something that I could just just a day or two ago, just spin up and go right through. And thank you so much for, making this an open source project that we can do this kind of interesting stuff with and play with.
Absolutely. And
we are right
go ahead, Eric.
I can say that it's incredible contribution, because I mean, this is not only the containerization, but it's a demonstration of the whole toolchain from running input deck, which is another solver deck directly with Radioss, showing this functionality, how to set up also before the let's say the Apptainer, the how to compile the source code, as you said, and thanks a lot, Dave, for the lesson about Apptainer, very insightful for me. And also after the simulation to show how to use the converter to be able to run afterwards a ParaView, so to have a really full toolchain of open source product. So I mean that's excellent, and for sure, with OpenRadios, we really want to tackle many different domains. So you talked about materials failure, things like that. This is very important. Here, this is let's say classic car, but now we have electric car, so with battery pack. So it's even more complex, because you need to investigate what happens during the crash, but also post-crash with let's say potential thermal runaway after the crash, a long time after the crash. So it's very complex world, and having the ability to progress on those different type of domain, it's very important. And one domain is how to make the code also more efficient, how to make it easier to run it, to compile it, to optimize it. And I think that for that, Apptainer is one important piece. I think containerization is one thing that customers really ask more and more. And the fact to be able to demonstrate how to do it very easily with OpenRadios is something very appealing that we can apply also for the commercial version and for commercial customers. So thanks a lot for doing this demo, doing this how-to so very quick, and to be one of our first contributors to this project. And I already hope to have many contributions like that in the future. So yeah, very nice illustration.
It's fantastic. Thank you, Eric. And since we were up on time, I was going to have you give the last words anyway, but you did a fantastic job wrapping it up. And we really appreciate you spending the time and coming to talk to us. I appreciate all that you do. Yoshi, we really appreciate your work and effort too. Dave, thanks for putting it together. Jonathan, Forrest, Brock, good to see you again. Come back next week. Go ahead and like and subscribe, and we will see you later. Thanks for joining.
Thanks a lot. Bye-bye.